Okay, so we went from one neuron to start working with layers of these units. And remember, every time you see a neuron, you can imagine that it is a simple logistic regression model, the one that you work with in the second exercise. So the idea here is to have many layers of these neurons, okay, and the design of the network is also called topology. And in this case, we are looking at a network or multi-layer perceptron with two inputs. So this will represent how many features we are using for this problem. Then you have a layer of what we call hidden units. So this will be a hidden layer. You can have many hidden layers. In this case, we have only one. And then we have the output layer. Okay, so we always say we have an input layer, which are the features, the output layer, and several hidden, possibly several hidden layers. So this will be a topology of 2 times 2 times 2. Okay, and in the each of the neurons, remember that you will need to add a bias, because each of these will be a function, and we need to let these curves or lines or hyperplanes to go up or down. So to train these models, to update the weights of these models, we can divide the algorithm in 2 stages. The first one is the propagation. So you take one of the examples. Suppose that you take one of these examples of the animals, and you put the values of feature 1 here and the value of feature 2 here. Once you have the values here, you evaluate the input of neuron 3. Each of these arrows represent weights, so each of these will have a different weight. So you can compute the big sigma, the input of this neuron. Once you have computed the input of this, you apply your activation function, and you will get a number between 0 and 1. That output is sent to the next layer of neurons. Okay, in this case 5 and 6, and the output of 3 will become an input of 5 and an input of 6. In the same way, we do this the same propagation with neuron 4. So the value of feature 1 will be fed into neuron 4. The same happens with feature 2. We compute the input, the big sigma, then the small sigma, which is the activation, and we send the output as an input of neuron 5 and as an input of neuron 6. And then we continue with neuron 5. Neuron 5 will get one input from neuron 3, one input from 4, and the bias, and the big sigma, the input, will be evaluated in this small sigma, which is the sigmoid, and then you will get a number between 0 and 1. Here I am representing this as a set, which could take values only 0 and 1. And during the training, you need to consider the number that is going out in this. So you can get a number between 0 and 1. You will usually get decimal numbers. Okay, so you will get 0.56 or 0.37, whatever. So during the training, you need to consider that number to update the weights of your network. But once the model is trained, and this is what I wanted to represent here, if you want to classify a new input, when you get the output here, if the output is 0.5 or larger than 0.5, you will consider that this output is giving you a number 1. Otherwise, if the output is less than 0.5, you will consider it as a 0. So when you are using the network for classifying, you can consider only 2 possible numbers, 0 and 1. Okay, but remember, this is only when you have already trained the model and you are using the model to do a new classification. So this first stage is called the propagation. So you take an example and propagate the input signal going forward from the input neurons to the output neurons, passing through all the hidden neurons. I prefer to draw these diagrams from left to right, but you can see in some publications that they draw it from bottom to top, and that's why they started calling these deep models, because they go deeper, adding more hidden layers. So in the second stage, after you have propagated the input, so you have evaluated one example and you have the output here, you perform the back propagation, which is to go backwards, and as you go backwards you update or make changes to the weights of the network, but you need to do it in this topology from right to left. So you propagate the error of the network with respect to the current example, going backward from the output neurons to the input neurons, passing through all the hidden neurons. So here we're talking about supervised learning. So for any example, you will have an input and what you want as an output. So initially, all the weights are generated randomly. Also, you should initialize these values in a small interval around 0, because we are going to update the weights many times, and we don't want these weights to grow very fast. So when you evaluate or propagate one example, for that example, you know, in this case, if that example should give you a 1 here or a 0, and the same here with this output. So when you evaluate it with the randomly generated weights, you will get, of course, basically a random output here, always between 0 and 1. If you get, for example, here in neuron 5 an output value of, let's say, 0.3, and for that example you should get a number 1, then just by knowing that the target value is 1 and you are getting 0.3, you can already see how big your error is just by computing the subtraction of 0.3 minus 1. So you will get an idea of how wrong this neuron is, and the same happens with every output unit. So that error, that difference between what you are getting as an output in 5 and 6 and what you want these neurons to output, this is the error that they say here. You back propagate the error. Okay, and we're going to see the rules that you need to program to do this back propagation of the error. So here we talk about deltas. Delta 5 in this case will represent the error of our neuron 5, and the error of neuron 5 is computed with these two products, which is the output of neuron 5 times 1 minus the output of neuron 5 times the error that we mentioned before, the output error. Now this is very obvious. This is what I explained before. This is what you want neuron 5 to output, This is the target value, and this is what the current network is outputting in this neuron 5. Okay, so this is very intuitive. These two factors here come from the derivative of the sigmoid function. So if you remember, the derivative of the sigmoid function is in terms of the same sigmoid function, and it was the evaluation of the sigmoid function, which is actually what you are getting here, the evaluation of the sigmoid, times 1 minus the same sigmoid function. So this comes from the derivative of the activation function. If you decide to use, for example, tangent hyperbolic instead of sigmoid, then this rule is going to change. So if you want to work with different activation functions, you need to compute the derivative of that function, so you will get your new way to compute the delta of any of the neurons. One important thing that you will see is that there is a way to compute the deltas of the neurons depending on whether the neuron is an output neuron or a hidden neuron. So in this specific case of output neurons, we know what we want our neuron to output, which is the label or the target value, and we know what the neuron is outputting in this moment. So we can make this subtraction. But you will see that when we try to compute the delta of, for example, this neuron, this hidden neuron 3, nobody is going to tell you what is the number that should go out of neuron 3. So you will see that the deltas will be computed different here. But at this moment, just consider that this way to compute the delta of output neurons is the same for any output neuron. Okay, so once you have computed the error of neuron 5, then you can modify or update the weights of the connections that are going into neuron 5, which in this case will be this rule. And you will see here that in this notation here, weight 5,3 means the weight that goes into 5 coming from 3. Okay, so this W 5,3 is making reference to this weight. So in this rule, you will give the same current value plus some learning rate, some alpha fraction of the error of neuron 5 times the output of neuron 3. So the output of neuron 3 is the signal that is going through this connection. In the same way, we can compute W 5,4, which is this rule, which will be the same value plus some alpha of delta 5 times the output of neuron 4. Okay, and these rules will be the same for neuron 6, and if you had more neurons here, you will apply the same rules. You just need to see carefully where are the connections coming from. Now, if you are updating hidden neurons, and by the way, you need to update all the output neurons, which is the last layer of neurons, and then you can start updating the weights of the hidden units, of the hidden layers. So in this case, we have only one hidden layer, so we will update the weights of these two neurons. But if we had one more layer over here, we will need to first compute or update the weights of these two neurons, 3 and 4, before you can modify the weights of the neurons in the previous hidden layer. Okay, so that's why you need to back propagate. You need to go from the last layer to the first one. So in the case of hidden neurons, okay, first just to clarify this delta k means the error of neuron k, output of k, which in this case will be the evaluation of the sigmoid of the big sigma of k. Yk represents the desired output, the target value of neuron k. Wij is the connection that goes from j to I, and alpha is just a learning rate. Okay, now let's talk about the hidden neurons. We need to compute the delta of 3, and the delta of 3 will be first the derivative of the sigmoid, which is output of 3 times 1 minus output of 3. And as I said before, in these hidden neurons we don't have information about what should be going out here. Okay, so the way the backpropagation algorithm solves this problem is to consider the errors of the neurons in the next layer, like in this case the output layer, giving them some weight to each of these deltas. So in this rule, for example, for delta 3, we have two outputs. One output, or it's only one output, but this output is going to 5 and it is also going to 6. So we need to consider some the weight of the connection. We need to multiply it by the error of the neuron where this connection is going to. So we will have W53 times the error of neuron 5 plus W6,3, so the weight, the value of this weight times the delta of 6. If we had, for example, neuron 7 here, we will need to add plus the connection going from 3 to 7 times delta 7. Okay, so that's why you need to compute the deltas of the output layer, because otherwise you cannot compute the delta of the previous hidden layer. And once you have computed delta of 3, then you apply the same rule that we just for output neurons. We just add to the current value of, for example, 3,1, which will be this, some alpha portion of delta 3 times the output of neuron 1. In this case, the output of neuron 1 is our feature 1. Okay, but if you had here another hidden neuron, we will be making reference to the output of this neuron. In this case, it's just the input feature 1, and the same for the weight going from 2 to 3. So this algorithm it is quite powerful, and this is an example of a quite old project or experiment that was the idea of this experiment was to train a neural network to detect if a person is looking to the left of himself, if the person is looking just forward to his or her right side, or if the person is looking up. So they trained a neural network with 960 inputs with one hidden layer of 3 neurons and 4 output neurons. So these 960 inputs were because they were using images of sizes 30 times 32. So you were getting 960 pixels. So each of the inputs or each of the features in this network is the value in grayscale of the pixel, okay, going from 0 to 1. So each input is one of the pixels in this image. Then they had only 3 hidden neurons in only one hidden layer, and the output were 4 because they trained this network in such a way that the output neuron 1 activated when the people was looking to the left. When the people was looking right, was activated only the second neuron. Then if the person was looking right to the right, only the third neuron was activated. And if the person was looking up, only the fourth neuron was activated. So they trained this with 260 images in the dataset, and they managed to get a 90% of performance. So in these plots here, you can see how after only one iteration of the backpropagation algorithm, the network is still having problems to classify the images. So in this case, you get activations in 3 neurons, in 3 output neurons. So here you can see that there are 4 squares. Maybe here is more clear. This is this represents the value of the output of the first output neuron. This is the value of the output of the second neuron. The third corresponds to the third neuron, the third output neuron, and this is the fourth output neuron. And 0, white represents number 1, which is the maximum amount of light that you will get in a pixel. So it will make a very clear or light pixel, and 0 represents 0 light. Okay, and any gray value will represent a number between 0 and 1. So when you get a 1, like in this case, it represents that the neuron is getting activated. Okay, so initially the network is not trained very well, of course, with only one iteration, but after 100 iterations, then you can see here that for every given image as an input, only one of the neurons was activated. Like in this case, the first neuron was activated. In this case, the last one. This case, the third one, and here the second one. So after only 100 iterations, the network was trained to classify images in this way.